Human colonization of Mars is more than just a technological challenge, it is a scientific experiment on planetary scale. Scientists envision domed habitats, underground living spaces to protect from radiation, and hydroponic farms providing fresh food. Every aspect of life must be adapted to the Martian environment. Medical research is underway to understand how reduced gravity affects muscles, bones, and the cardiovascular system over long periods. Experiments on the International Space Station and simulated habitats on Earth provide critical data for designing sustainable Martian communities. Even social and cultural factors are studied: how small, isolated crews interact, make decisions, and maintain morale will determine the success of early colonies. Mars is not the only target for human colonization, though it is the nearest and most feasible. The Moon is being revisited as a proving ground for technologies and practices that will later be used on Mars. Lunar bases will test life support systems, construction techniques, and surface mobility in a low-gravity environment. They will serve as staging areas for deeper space missions, providing opportunities to mine resources, assemble spacecraft, and practice long-term living away from Earth. The Moon is both a destination and a laboratory, helping humans prepare for the more challenging environments of Mars and beyond. International collaboration plays a crucial role in preparing for human missions to Mars. Space agencies from the United States, China, Europe, Russia, and private companies are developing rockets, habitats, life support systems, and surface vehicles. Projects like SpaceX's Starship aim to transport humans and cargo to Mars, while NASA Artemis program focuses on returning humans to the Moon and testing technologies for interplanetary travel. Collaboration ensures that expertise, technology, and resources are shared, making ambitious projects more feasible. It also reflects the broader humanistic value of space exploration, transcending national boundaries to achieve goals that benefit all of humanity. The philosophy behind Mars exploration extends beyond science and technology. Mars represents humanity's first step toward becoming a multiplanetary species. Learning to live sustainably on another world will teach lessons about resilience, adaptation, and stewardship. It challenges humans to reconsider how resources are used, how societies function in isolated environments, and how to maintain the delicate balance between exploration and preservation. Mars exploration is not simply about colonizing a planet, it is about expanding the capacity of humans to survive, thrive, and coexist with new environments. Preparing for deep space travel requires understanding not only Mars but also the broader solar system. Advanced propulsion methods, such as nuclear thermal and electric propulsion, could reduce travel times and increase efficiency. Radiation shielding, artificial gravity, and closed-loop life support systems will be essential for journeys to the outer planets or even to distant moons of Jupiter and Saturn. Missions to these distant worlds will rely on the knowledge gained from Mars and the Moon, how to live, work, and maintain human health in environments far from Earth. Every step taken closer to Mars is a step toward humanity's long-term presence in the solar system. The scientific payoff of human exploration is enormous. Astronauts on Mars can perform experiments on site, drilling deep into the planet's crust, analyzing rocks and ice, and searching for evidence of past life. They can deploy instruments, collect samples, and test technologies that would be impossible to operate remotely. Human presence increases the speed, flexibility, and adaptability of scientific exploration, allowing discoveries that robotic missions alone could not achieve. The combination of human ingenuity and robotic precision maximizes scientific return while preparing humanity for future endeavors across the solar system. The cultural significance of Mars exploration is equally profound. The first human steps on Mars will inspire generations, fuel curiosity, and reinforce the value of scientific discovery. It will become a symbol of what humans can achieve when imagination, technology, and perseverance converge. Art, literature, and education will reflect the human connection to Mars, just as the moon landings influenced culture in the 20th century. Mars exploration is not just a technical milestone, it is a defining moment in the human story, representing the enduring desire to explore, understand, and expand the boundaries of what is possible. Mars colonization also underscores the importance of sustainability and ethical exploration. Humans must ensure that any settlement respects the planet's environment, preserves potential biosignatures, and minimizes contamination. Responsible exploration is a guiding principle reflecting humanity's broader responsibility to its home planet, other worlds, and future generations. Colonizing Mars is not about conquest, it is about learning to live in harmony with new environments while expanding human knowledge and capability. As Segment 3 begins, it becomes clear that Mars is both a destination and a laboratory for the human species. It tests technological limits, pushes scientific inquiry, and challenges human resilience. Robotic missions prepare the way, providing the knowledge and tools necessary for safe exploration. Human missions will follow, building habitats, conducting experiments, and pioneering the first steps of permanent human presence beyond Earth. Every experiment, every rover traverse, every spacecraft landing contributes to the cumulative knowledge that will make Mars colonization possible. Ultimately, Mars exploration represents humanity's transition from a planet-bound species to an interplanetary one. It combines engineering, science, psychology, culture, and philosophy into a single endeavor, demonstrating the multifaceted nature of space exploration. The lessons learned on Mars will inform travel to distant moons, asteroids, and eventually other star systems. Mars is not just a destination, it is the bridge between Earth and the stars, the first chapter in humanity's journey into deep space, and a testament to curiosity, courage, and the enduring drive to explore the unknown. While Mars represents the nearest frontier for human colonization, the moons of Jupiter and Saturn offer a more distant, yet tantalizing, set of challenges and opportunities. Europa, with its subsurface ocean, is considered one of the most promising candidates for extraterrestrial life. Human missions there are still decades away, but concepts are being developed that combine orbital spacecraft, landers, and even submersible probes capable of penetrating the icy crust. Radiation near Jupiter is intense, far exceeding what humans experience on Mars, so any mission would require highly specialized shielding, carefully timed exposure, and advanced robotics to reduce human risk. Astronauts might operate from orbit, remotely controlling robotic vehicles to explore Europa's ocean beneath the ice, testing the limits of autonomy, precision, and endurance. Enceladus, Saturn's moon, is another prime target. Its geysers eject water vapor and ice into space, offering a relatively accessible way to sample its ocean without drilling through kilometers of ice. Human missions might focus on orbiting spacecraft that collect plume material, study its chemical composition, and scout potential landing sites. Titan, Saturn's largest moon, presents a completely different environment, a thick, nitrogen-rich atmosphere, methane lakes, and a surface where human explorers would need floating habitats, pressurized vehicles, and systems capable of handling extreme cold. Each moon presents unique engineering challenges, pushing the boundaries of spacecraft design, habitat construction, and life support systems. Advanced propulsion is critical for these ambitious missions. Traditional chemical rockets, while reliable for Earth orbit and Mars missions, are too slow for consistent travel to Jupiter, Saturn, or beyond. Nuclear thermal rockets could provide higher thrust and efficiency, drastically reducing transit times. Ion drives, already used on spacecraft like Dawn, offer long-duration, fuel-efficient acceleration, making interplanetary travel feasible over months or years. Laser-propelled microcraft, though still theoretical, could reach nearby star systems within decades. These propulsion technologies, combined with robotic precursors and autonomous systems, provide a roadmap for humanity's journey from Mars to the outer solar system and eventually to interstellar space. Long-duration human missions also require innovation in life support, artificial gravity, and health management. Radiation shielding may involve water walls, magnetic fields, or specially engineered materials. Habitats must recycle air, water, and food efficiently with redundancy to prevent system failure. Artificial gravity, created through rotation or other methods, could reduce the debilitating effects of microgravity on muscles, bones, and the cardiovascular system. Psychological well-being is equally crucial. Crews must maintain social cohesion, manage stress, and find ways to feel connected to Earth despite months or years of distance. Space agencies and private companies are testing solutions through analog missions in deserts, polar regions, underwater laboratories, and orbital platforms. These experiments build the foundation for safely sending humans far beyond Mars. Interstellar travel represents the greatest challenge humans have ever faced: vast distances, limited resources, extreme isolation, and the need for self-sufficiency. Even the nearest star system, Alpha Centauri, is over 4 light-years away. At current spacecraft speeds, that distance would take tens of thousands of years to cross. But concepts under study such as laser-propelled nanocraft, nuclear fusion propulsion, and advanced ion engines could shrink the travel time to mere decades or centuries. These concepts remain theoretical but inspire engineers, scientists, and dreamers alike, reminding humanity that imagination and innovation are the seeds of future exploration. Preparing humans for multi-year or even multi-decade missions requires solving unprecedented challenges. Life support systems must be almost entirely self-sufficient, capable of recycling air, water, and nutrients without resupply from Earth. Energy must come from renewable or nuclear sources sufficient to power habitats, propulsion, and scientific instruments. Radiation shielding is critical. Cosmic rays and interstellar particles pose risks far beyond anything experienced in low Earth orbit or even near Jupiter. Artificial gravity, through centrifugal habitats or other engineering solutions, may be necessary to maintain health over long durations. Psychological well-being is equally crucial. Crews will face isolation, confined spaces, and limited communication with Earth. Preparing for these missions involves careful training, analog simulations, and robust planning for emergencies and unexpected challenges. Robotic missions will pave the way for interstellar human exploration. These precursors could map planetary systems, test propulsion and communication technologies, and return data to ensure that human travelers avoid hazards. Autonomous probes could scout habitable planets, analyze atmospheres, and identify resources such as water or minerals. This combination of robotic reconnaissance and human ingenuity will be essential. No spacecraft can rely solely on Earth-based control when light years of distance create communication delays of years. Human presence will eventually follow the robotic groundwork, capable of adapting, repairing, and making decisions that machines alone cannot. The philosophical implications of interstellar travel are profound. Humanity will confront questions of identity, purpose, and our place in the cosmos. What does it mean to leave the solar system, possibly never returning to Earth? How do we preserve culture, knowledge, and social structures across generations? These missions are not just technical challenges, they are exercises in human resilience, ethics, and long-term planning. Preparing for interstellar exploration requires a vision that spans centuries, combining science, engineering, philosophy, and imagination into a single coordinated effort. Interstellar missions also emphasize the importance of sustainability and stewardship. Even on long-duration solar system missions, humans must minimize waste, recycle resources efficiently, and maintain harmony within small communities. On interstellar missions, these lessons become magnified. Every action, every resource allocation, every decision could determine the survival of a crew and the success of the mission. Preparing for this requires innovation in materials, energy, recycling, and governance, building systems that are reliable, redundant, and adaptable to unforeseen challenges. As humans expand into the solar system and begin contemplating interstellar travel, collaboration becomes essential. Nations, private companies, and international scientific organizations must work together to share expertise, technology, and knowledge. Just as the International Space Station demonstrated global cooperation in low Earth orbit, future missions will require partnerships that span continents and generations. Pooling resources reduces risk, accelerates progress, and ensures that the benefits of space exploration are shared across humanity rather than being the possession of a single nation or corporation. Interstellar exploration also challenges humans to rethink the concept of time. Missions may last multiple generations, requiring solutions for education, governance, social cohesion, and culture. Crews may live and die aboard the spacecraft, raising questions about how to preserve knowledge, maintain morale, and ensure continuity. Long-term mission planning will rely not just on engineers and scientists but on psychologists, sociologists, educators, and ethicists. Preparing humanity for life beyond the solar system is as much a social challenge as a technological one. Despite these challenges, interstellar exploration embodies humanity's enduring curiosity, the same drive that led to the first telescopes, the first satellites, and the first human steps on the moon now inspires plans to reach the stars. It demonstrates that exploration is not confined by immediate feasibility, it is guided by vision, ambition, and the desire to expand knowledge. Each robotic mission, each Mars landing, and each orbital experiment builds experience, tools, and confidence that one day may make interstellar travel possible. The journey is gradual, cumulative, and interdependent, combining incremental progress with long-term vision. Segment 3 also highlights that human expansion into space is more than a technical exercise, it is a profound transformation of human perspective. As astronauts travel farther from Earth, they will see their home as a fragile, small, blue world suspended in darkness. This overview effect, reported by astronauts in low Earth orbit, fosters a sense of shared destiny, environmental stewardship, and global unity. Interstellar exploration amplifies this perspective, reminding humanity that Earth is a singular oasis and that survival beyond it requires cooperation, foresight, and humility. Ultimately, Segment 3 shows that human exploration from Mars to the moons of Jupiter and Saturn, and ultimately to other star systems, is a story of courage, curiosity, and cumulative effort. Robotic missions prepare the way, technologies advance capabilities, and philosophical, ethical, and cultural considerations guide responsible exploration. Each mission builds on the last, forming a continuous trajectory toward greater knowledge, longer durations in space, and eventual human presence among the stars. Mars is the first stepping stone, the outer planets are the next challenge, and interstellar ambitions represent humanity's ultimate horizon. Exploration is incremental, visionary, and inseparable from what it means to be human, a species defined by the desire to reach beyond, to understand, and to expand the boundaries of possibility. The story of Segment 3 is therefore not only about technology or survival, it is about identity, resilience, and imagination. Humanity is learning to live beyond its birthplace, to adapt to extreme environments, and to build communities in places where no one has ever lived before. It is preparing to confront the unknown, to endure the vast distances of space, and to carry knowledge, culture, and curiosity into the depths of the universe. Each rover, each habitat, and each spacecraft is a testament to human ingenuity and determination, laying the foundation for generations of explorers who will continue the journey. Segment 3 concludes by emphasizing that Mars, the Moon, outer moons, and interstellar ambitions are interconnected milestones. Each challenge teaches lessons for the next, forming a chain of exploration that extends humanity's reach. Technology, science, philosophy, and culture converge to enable survival, growth, and discovery. The red planet is the first chapter, the icy moons are the next, and the stars are the horizon. Exploration is ongoing, incremental, and cumulative, demonstrating that humanity's destiny is to expand outward, fueled by curiosity, courage, and the timeless drive to know the unknown. As humanity looks beyond Mars, the future of space exploration becomes a story of possibilities, technologies, and bold ambitions that once seemed like science fiction. Advanced spacecraft, sustainable habitats, and interplanetary infrastructure are no longer just ideas, they are actively being developed and tested. Concepts such as self-replicating robots for construction, modular habitats that expand like building blocks, and autonomous systems capable of repairing and maintaining equipment on distant worlds are central to long-term colonization. The Moon and Mars serve as proving grounds for these technologies, allowing engineers to learn how structures, energy systems, and life support work in low gravity and harsh environments. These innovations are the foundation for even more ambitious goals, including terraforming, asteroid mining, and eventually establishing permanent human societies across multiple planets. Terraforming, the process of modifying a planet or moon to make it habitable for humans, represents one of the most ambitious challenges in human history. Mars, with its thin atmosphere and cold temperatures, is the primary candidate for early terraforming experiments. Scientists imagine methods such as releasing greenhouse gases to thicken the atmosphere, melting polar ice caps to create liquid water, and using mirrors in orbit to direct sunlight onto the surface. While these ideas are theoretically possible, the engineering, energy, and ethical challenges are enormous. Terraforming would take centuries, if not millennia, and would require technologies far beyond current capabilities. Yet even preliminary steps, like warming local regions or producing oxygen through chemical and biological processes, could make human habitats safer and more self-sufficient. Asteroid mining represents another frontier in space technology. Asteroids contain vast amounts of metals, minerals, and water resources that are rare or expensive on Earth. Water extracted from asteroids can be split into hydrogen and oxygen to create rocket fuel, enabling refueling stations in space that reduce the need for Earth-based launches. Metals like iron, nickel, and platinum can be used for construction, electronics, and manufacturing in space. Companies and space agencies are developing robotic prospectors to identify promising targets, autonomous mining equipment to extract resources, and orbital processing facilities to refine materials. Asteroid mining not only provides essential resources for long-term space missions, but also opens the door to a space-based economy where raw materials are sourced and utilized beyond Earth. Energy is a critical factor in all future space endeavors. Solar power remains the most reliable source in the inner solar system, but nuclear reactors and fusion energy may become essential for missions to the outer planets or interstellar travel. Space-based solar power could even transmit energy back to Earth, creating a system where space becomes both a source of exploration and a solution to energy scarcity. Developing efficient, renewable, and scalable energy systems is central to enabling humanity to live and thrive on multiple worlds. Energy powers everything from life support to propulsion, mining to manufacturing, and will determine the speed and scope of human expansion into space. Life support and habitat technology are evolving rapidly. Closed-loop systems that recycle air, water, and nutrients are critical for survival on Mars, the Moon, or deep space stations. Hydroponics, aeroponics, and algae-based oxygen production systems allow food to be grown in confined spaces with minimal resources. Habitats may be modular, expandable, and shielded from radiation using regolith, water, or magnetic fields. Long-term habitation requires redundancy, reliability, and the ability to adapt to changing conditions. Innovations tested in orbit and on Earth like biospheres, underwater labs, and Antarctic research stations provide lessons in isolation, resource management, and group dynamics that will guide multiplanetary living. The societal implications of becoming a multiplanetary species are profound. Space colonization is not just a scientific or technological endeavor, it will transform culture, economics, and human identity. Humans living on Mars or the Moon will develop new social norms, governance structures, and ways of interacting. Education, law, and communication will need to adapt to life far from Earth. Economies will emerge around mining, manufacturing, and research, and a space-based society may eventually operate with a degree of independence. Understanding how humans function in these environments psychologically, socially, and politically is as important as understanding the engineering of habitats and spacecraft. Cultural and philosophical questions also arise. What will it mean to be human when entire communities exist on other worlds? How will art, literature, and identity evolve when people no longer share a single home planet? Will humanity develop a planetary or even interplanetary consciousness, sealing itself as a species spread across the solar system rather than confined to Earth? These questions are not abstract, they influence mission planning, social cohesion, and the long-term sustainability of space settlements. Preparing humans to thrive in new environments requires addressing not only physical survival, but also mental, emotional, and cultural well-being. Legal and ethical considerations are critical in shaping the future of space. Treaties like the Outer Space Treaty establish that no nation can claim ownership of celestial bodies, but as mining, colonization, and permanent settlements become possible, new legal frameworks will be necessary. Questions of resource allocation, environmental protection, and interplanetary governance will need clear guidelines. Humanity must balance ambition with responsibility, ensuring that space exploration preserves potential life, respects extraterrestrial environments, and avoids conflict. Ethical exploration is a cornerstone of sustainable expansion, reminding humans that reaching the stars is not only about capability, but also about stewardship. The future of transportation in space is equally transformative. Space elevators, electromagnetic launch systems, reusable rockets, and advanced propulsion like nuclear, thermal, or fusion engines could dramatically reduce travel time, cost, and risk. Interplanetary cargo routes may operate like trade highways, connecting Earth, the Moon, Mars, and asteroid belts. Rapid travel will enable supply chains, research collaboration, and emergency response between worlds. Mastery of transportation technology will define the speed and scale of human expansion into the solar system. Artificial intelligence and robotics will be indispensable in the future of multiplanetary living. Robots will perform construction, maintenance, resource extraction, and exploration tasks, operating in environments too dangerous or remote for humans. AI systems will monitor habitats, optimize resource usage, and assist in decision-making, ensuring safety and efficiency. Humans and machines will work together, complementing strengths, mitigating weaknesses, and enabling sustainable living beyond Earth. Ultimately, humanity is entering an era where life beyond Earth is increasingly feasible. Mars, the Moon, asteroids, and eventually the outer planets will become part of a network of human presence, interconnected by technology, culture, and shared ambition. Space will no longer be an unreachable void, it will become a stage for human ingenuity, resilience, and adaptation. Colonization, terraforming, and resource utilization are steps toward becoming a multiplanetary species, but they also teach lessons about sustainability, cooperation, and ethics that apply back on Earth. The long-term vision of humanity in space is both technical and philosophical. Technology enables survival, exploration, and growth. Culture, law, and ethics shape how humans interact with each other and with new worlds. Science provides knowledge and understanding, guiding safe and responsible expansion. Together, these elements create a roadmap for humanity's future, a species that reaches beyond its cradle, adapts to extreme environments, and spreads knowledge, culture, and life across the solar system. Terraforming Mars begins with small, achievable steps before attempting planet-wide transformations. Scientists and engineers focus on localized experiments that make certain regions more habitable. For instance, greenhouse habitats covered with transparent domes could trap heat, allowing plants to grow in Martian soil and creating oxygen-rich environments for humans. Subsurface habitats could use natural lava tubes for shelter, providing insulation from radiation and temperature extremes. Artificial magnetic shields are being studied to protect the planet from harmful solar and cosmic radiation, gradually making the surface safer for extended human activity. Asteroids provide critical resources that support these terraforming efforts. Water-rich asteroids could supply hydrogen and oxygen for rocket fuel or life support systems. Metals like iron, nickel, and platinum can be used to construct habitats, mirrors for orbital solar reflexes, or even components for fusion reactors. Mining operations will initially rely on robotic systems and AI, reducing human exposure to danger. Advanced manufacturing techniques, including 3D printing in microgravity, could turn raw asteroid material directly into habitat structures, solar panels, or spacecraft components. Over time, asteroid mining could support a self-sufficient, interplanetary industrial base, reducing reliance on Earth for resources and enabling large-scale terraforming projects on Mars and other worlds. Interplanetary governance and society will evolve alongside technology. Laws and treaties will need to define resource rights, territorial claims, and environmental protections for Mars, the Moon, and asteroids. New governance structures may emerge in orbital habitats, combining Earth-based laws with local councils to address the unique challenges of living far from home. Decision-making in isolated colonies will require balance between efficiency and democracy, ensuring fairness while maintaining operational safety. Social systems must adapt to communication delays with Earth, relying on autonomous governance, clear protocols, and cultural norms designed for long-duration isolation. Education, culture, and identity will also adapt to multiplanetary life. Children born on Mars or in orbital habitats will grow up with different day lengths, gravity, and environmental conditions. Their educational systems will combine Earth-based knowledge with survival skills specific to their world. Language, art, and storytelling will evolve, reflecting new experiences and perspectives shaped by life beyond Earth. Shared cultural identity, even across different planets and habitats, will be vital for cohesion, cooperation, and long-term sustainability. Economic activity in space will create a new interplanetary society. Trade routes will connect Mars, the Moon, and asteroid colonies, moving water, fuel, metals, and manufactured goods. Interplanetary commerce will incentivize innovation in mining, manufacturing, energy, and transportation, creating new industries that do not exist on Earth. Markets may develop independently of terrestrial economies, operating on supply, demand, and logistics unique to the solar system. Economic activity will sustain growth, fund scientific research, and support the development of advanced habitats and infrastructure. Energy management will remain central to interplanetary civilization. Solar power, nuclear reactors, and eventually fusion will provide electricity for habitats, industry, and transportation. Energy will be stored, transmitted, and shared between colonies, creating a solar system-wide network that enables cooperation, growth, and resilience. Advanced power systems will allow colonies to expand, support more residents, and power industrial activities such as asteroid mining or Martian manufacturing. Efficient energy use is not just practical, it is essential for survival and long-term sustainability in space. Technology, society, and culture are deeply intertwined in multiplanetary life. Robotics and AI will continue to handle high-risk tasks, monitor life support systems, and assist humans in daily operations. Humans will focus on creativity, problem-solving, exploration, and community building. Education will emphasize survival skills, science, engineering, and social cooperation, preparing younger generations for life on Mars, in orbit, or on asteroids. Cultural identity will evolve as humans adapt to new worlds, preserving traditions from Earth while embracing experiences unique to their habitats. Music, art, literature, and storytelling will reflect the challenges and wonders of life among the stars. Ethics and sustainability remain guiding principles. Colonists must minimize environmental impact, avoid contaminating planets, and preserve potential biospheres. Decisions about resource use, expansion, and exploration will require careful planning and coordination. Ethical frameworks will ensure that interplanetary civilization grows responsibly, balancing ambition with preservation, independence with cooperation, and innovation with accountability. These principles will define the legacy of humanity's expansion beyond Earth. Over centuries, settlements on Mars, the Moon, and asteroids could evolve into fully self-sufficient societies. Martian cities might span entire valleys with interconnected domes, transportation systems, agriculture, and research facilities. Asteroid hubs could host rotating communities with industrial, residential, and recreational spaces carved from rock. Orbital stations could become centers of trade, education, and governance, linking multiple colonies in a network of communication and commerce. Together, these communities would form a solar system-wide civilization, connected by trade, energy, technology, and culture. Segment 4 highlights that human civilization is no longer confined to a single planet. The expansion into space transforms humanity into a multiplanetary species capable of surviving and thriving in extreme environments. Terraforming projects on Mars, asteroid colonies, interplanetary trade, governance structures, and cultural evolution all work together to create sustainable, resilient societies. Each innovation, settlement, and mission contributes to a network of interdependent systems that support life, knowledge, and culture far from Earth. Ultimately, Segment 4 shows that the journey to a multiplanetary future is both practical and philosophical. Technology enables survival, resource management, and infrastructure. Economics drives innovation and sustainability. Governance, culture, and ethics shape identity, cohesion, and long-term viability. Humanity is learning to adapt to new worlds, solve unprecedented challenges, and create societies that thrive far beyond Earth. Mars, asteroids, and orbital habitats are not just destinations, they are steps in the evolution of civilization. Exploration, cooperation, creativity, and responsibility remain the guiding principles, showing that the dream of humanity as a multiplanetary species is not merely a vision, it is becoming a reality. Humanity's journey into space has transformed from an ambitious dream to a practical reality, but the ultimate frontier lies beyond our solar system. Interstellar exploration represents the next stage of human expansion, a challenge that will require extraordinary advances in technology, science, and human cooperation. Distances between stars are immense. Even the nearest star system, Proxima Centauri, is over 4 light-years away. Current chemical rockets would take tens of thousands of years to reach such destinations, so entirely new propulsion methods are being envisioned. Concepts like nuclear fusion propulsion, antimatter drives, and even theoretical warp or light sail technologies may one day allow humans to travel between stars within a human lifetime. These ideas, while speculative, demonstrate the scope of ambition required to reach the stars. The first steps toward interstellar travel may involve sending robotic probes and AI-driven explorers to nearby star systems. Missions like Breakthrough Starshot aim to send tiny spacecraft accelerated to a fraction of the speed of light, carrying instruments capable of capturing images and data from distant exoplanets. These missions serve as both scouting expeditions and technological experiments, teaching humanity how to navigate, survive, and operate in interstellar space. The data collected will inform the design of future crewed missions and allow scientists to identify potentially habitable exoplanets that could serve as new homes for humanity. Long-term interstellar travel requires self-sufficient, closed-loop habitats capable of supporting life for decades or centuries. Generation ships, massive spacecraft in which multiple generations live and die during the voyage, are a theoretical solution. These ships would need recycling systems for air, water, and food, sustainable energy sources, and robust social and governance structures. Education, healthcare, and culture would need to be maintained across generations, ensuring continuity of knowledge, skills, and identity. Humans aboard such vessels would develop a unique culture, shaped by isolation, shared purpose, and the vast emptiness of space surrounding them. Interstellar exploration also raises profound philosophical and ethical questions. What does it mean to leave Earth, our cradle, and travel into the unknown? How do we define humanity when communities exist light years away from our home planet? These questions are not merely abstract, they influence mission planning, resource allocation, and the social structures needed for long-duration space travel. Humanity's expansion into interstellar space will test the limits of our cooperation, creativity, and resilience, requiring unprecedented levels of foresight and responsibility. As humans reach other star systems, the concept of colonization extends beyond mere survival. New worlds will require careful adaptation, whether through constructing habitats in orbit, on moons, or on planets with tenuous atmospheres. Terraforming, while far more complex on exoplanets than on Mars, could one day become a reality with sufficient technological and energy resources. Water extraction, atmospheric modification, and local energy production will be essential. These settlements may start small as research stations or mining outposts, gradually expanding into self-sufficient cities capable of supporting generations of humans. Interstellar civilization will also demand a new framework for governance and ethics. The vast distances and communication delays between star systems will make centralized control impractical. Local autonomy will be essential, with colonies operating independently while maintaining shared principles of cooperation, safety, and sustainability. Governance may combine Earth-based laws with autonomous, consensus-driven systems, ensuring fairness and adaptability in environments where immediate support from Earth is impossible. Ethical principles will guide how humans interact with alien environments, potential life forms, and each other, preserving responsibility alongside ambition. Cultural evolution in interstellar communities will be profound. Humans living on distant worlds or generation ships will develop new traditions, art forms, and social structures shaped by isolation and the challenges of survival. Languages may evolve, storytelling may incorporate the vastness of space, and education will integrate knowledge from multiple generations. Cultural identity will remain critical, providing cohesion, shared purpose, and meaning to communities spread across light years of distance. These cultural adaptations will be as important as technology in ensuring the survival and thriving of humanity. Science will continue to drive human expansion. Colonists will explore distant planets, moons, and asteroids, searching for signs of life, studying planetary systems, and mapping new resources. Astrobiology may reveal entirely new forms of life, challenging our understanding of biology and evolution. Astronomy and physics will benefit from observations made from vantage points far beyond the solar system, allowing unprecedented clarity and perspective on the universe. Each mission, experiment, and observation will deepen humanity's understanding of the cosmos, fueling further exploration and inspiring future generations. Governance across interstellar distances will require unprecedented innovation. Centralized control from Earth will be impossible. Local colonies must operate autonomously while adhering to shared ethical and legal frameworks. Decisions will need to account for resource scarcity, emergencies, and long-term sustainability, balancing efficiency with fairness. Diplomatic mechanisms may emerge between star systems, coordinating trade, communication, and scientific collaboration. Ethics will guide resource use, environmental stewardship, and interactions with any potential alien ecosystems, ensuring that humanity's expansion does not repeat mistakes from Earth's history. Interstellar energy and resource management will define the capabilities of humanity. Fusion, antimatter, and advanced solar technologies could provide the energy necessary for long-duration missions, life support, and habitat expansion. Resource extraction from asteroids, moons, and planets will allow colonies to remain self-sufficient while contributing to interstellar trade networks. Efficient energy use will underpin civilization, allowing colonies to thrive despite extreme distances and isolation. Humanity's presence across the galaxy will transform philosophical understanding. The very concept of home will expand beyond Earth, incorporating multiple worlds and artificial habitats. Humans will confront questions about identity, purpose, and morality in new ways, learning to define themselves as a species rather than as residents of a single planet. Life among the stars will require cooperation, creativity, and ethical responsibility on scales never before imagined. Decisions made by one colony may affect others across decades or centuries, reinforcing the importance of foresight, planning, and shared values. Exploration, technology, culture, and ethics will converge to create resilient interstellar societies. Each colony will maintain its own social structures while participating in a broader human civilization. Artistic expression, education, governance, and science will evolve together, ensuring that humanity retains cohesion, adaptability, and shared purpose. Isolation will be balanced by communication networks, trade, and cultural exchange, fostering a sense of connection across unimaginable distances. Ultimately, Segment 5 presents a vision of humanity as a truly multi-star civilization, from Earth to Mars, from asteroid colonies to distant exoplanets. Humans will develop the tools, culture, and ethics necessary to thrive across the galaxy. Every settlement, every mission, and every technological breakthrough will expand the reach of life, knowledge, and creativity. Humanity will no longer be confined to a single world or solar system, but will carry its culture, curiosity, and responsibility to the stars. The legacy of interstellar exploration will extend beyond survival. Humans will reshape how they understand life, the universe, and their own place within it. Communities across the galaxy will demonstrate resilience, cooperation, and creativity, providing a model for long-term civilization that balances ambition with responsibility. Exploration, ethical stewardship, scientific inquiry, and cultural evolution will define humanity's presence among the stars, creating a civilization capable of enduring for millennia. Segment 5 concludes by showing that the journey of humanity into interstellar space is both practical and philosophical. Technology enables survival and exploration. Governance and ethics ensure stability, fairness, and responsibility. Culture, art, and education maintain identity, cohesion, and purpose. Science inspires innovation and knowledge. Together, these elements create a framework for life across the galaxy. Humanity is becoming a species defined not by a single planet, but by curiosity, cooperation, and the ability to adapt to environments far beyond its origin. Humanity's story in the cosmos will be one of endurance, ingenuity, and reflection. Colonies will grow, cultures will evolve, and knowledge will accumulate. Over generations, humans will spread across star systems, exploring new worlds, observing alien environments, and contemplating the universe on scales previously unimaginable. The expansion into interstellar space is not merely a journey, it is the continuation of humanity's quest to understand itself, its origins, and its destiny. Exploration, innovation, creativity, and responsibility will remain humanity's guiding principles. The stars will become the stage for human civilization, the laboratory for science, and the canvas for culture. humanity will carry the legacy of Earth outward, transforming distant worlds and reshaping its understanding of life and existence. The dream of becoming an interstellar species is no longer confined to imagination. It is the emerging reality of human ambition, resilience, and foresight. Segment 5 paints the final vision of a civilization that has expanded from a single planet to the stars, demonstrating that the drive to explore, innovate, and thrive is intrinsic to humanity. From the first steps on Mars to the creation of interstellar colonies, the story of space exploration is ultimately the story of human potential, curiosity, and the enduring desire to reach farther, learn more, and ensure the survival and flourishing of life across the cosmos.